Before we jump into Excel, let me introduce LP standard form. After we formulate an algebraic LP model, it is quite possible that some of the constraints cannot be easily formulated in Excel. To make it easier, we'd like to convert an LP model into its standard form. LP standard form has three criteria. First, all variables are on the left side of the constraint, and each variable appears at most one time in each constraint. Second, all constraints are gathered together and placed on the right side of the constraint. Lastly, gather all constraints of the same type together. Next, we're going to see an example of that. Here is an example. Suppose we have a constraint 3x1 plus 2x2 minus 3x3 divided by the sum of x1, x2, and x3 must be less than or equal to 0.9, assuming all variables are non-negative. It will be very difficult to formulate that directly in Excel. Instead, we can convert this constraint into this format. 2.1x1 plus 1.1x2 minus 3.9x3 less than or equal to 0. The standard form is much easier to handle in Excel. In our Blue Ridge example, the original algebraic model is already in its standard form. We'll then dive into Excel modeling directly. Since this is the first time we use Solver, let me show you how to install Solver add-in in MS Excel 2013 version. First, click File tab on the ribbon. Go look for Options. Click it. You will see Excel Options dialog window. Here, let's look for add-ins. It's right here. Click it. Then you're going to see a list of add-ins available. What we want is Solver add-in right here. Let's click it and then click Go. Now we can simply choose the add-ins we would like to add. Well, of course, we want to install Solver add-in. But because I already have Solver installed, I'm going to click Cancel. In your case, you're going to go ahead and click OK. Once you have Solver installed, go ahead and click Data tab. Under Data tab, you are going to see Solver. Now we're ready to go. To save time, here's the Excel template for our Blue Ridge example with most basic information already filled in. Let's take a look. In A column, we have some descriptions, such as unit profit, pump constraints, and so on and so forth. In B column, we have all the information about Aquaspa. B5 is where X1 is, and B6, of course, is Aquaspa's unit profit, and from B9 to B11, those are numbers with respect to the unit of resource a Aquaspa is going to need. Like one Aquaspa needs 1 pump, 9 hours of labor, and 12 feet of tubing. Similarly, in C column, we know that here C5 is where X2 is. Aquaspa has a unit profit of $300. It needs 1 pump, 6 hours of labor, 16 feet of tubing. E column shows the type of the constraint. In our case, all 3 constraints are of the less than or equal to type. And in F column, that's where the availability of resource is, or where the right-hand side value of constraint is. We have 200 pounds, 1566 hours of labor, and 2880 feet of tubing. Now let's go back and look at D column. That's where we need to do something about. First, let's look at total profit. That is our objective function. We know that our objective function is 350x1 plus 300x2, and we're gonna do that in Excel format. It's gonna be a formula, Excel formula. For any Excel formula, it starts with an equal sign. It's gonna be equal to B6 times B5 plus C6 times C5, and that is our objective function. And you can go ahead and click return. At this moment, because the starting values are 0, the resulting total profit is also 0. If you wish, you can change some of those numbers, and you will see the profit changes automatically. Well, before we move on, let me show you another way of formulating our objective function. In this case, our model is pretty simple. We have only 2 decision variables. But what if we have like 20 or 200 decision variables? Are we going to type a really long formula over here? Well, probably not. So here's what I'm going to do. I'm going to introduce to you a function called sum product in Excel. Here's what the sum product function does in Excel. Well, first, let's highlight one of the 2 arrays. Doesn't matter which one goes first. Let's say we highlight the objective coefficient array first, comma, second array, that's going to be the decision variable array. And close the parentheses. And what this function does in this case is simply what I did earlier. It is B6 times B5 plus C6 times C5. As you can tell, even if we have like 20 or 200 variables, we can use this function, and it gives us huge advantage. Return, and we get the number we saw earlier. Next, we're going to formulate the left-hand side of each constraint. Basically, in cell D9, that's how many pumps we are going to use. And we know it's x1 plus x2, right? So in Excel, once again, I'm going to use the function sum product. One array is the coefficient, 1 and 1. The other array is the variables. All right, here I'm going to do something slightly different. On a PC, I'm going to press F4. What you see happening over here is that dollar signs are added in front of B5, C5. What it does in Excel is called absolute cell reference. Let's close the parentheses. What absolute cell reference means over here is that all those constraints have very similar format. For pump constraint is 1x1 plus 1x2 less than or equal to 200. For labor constraint is 9x1 plus 6x2 less than or equal to 1566. Well, we see that coefficients are changing, but there's one part that does not change, which is our decision variables. So by adding dollar signs for B5 and C5, that means what? We're going to fix our decision variable. X1 will be in cell B5 and X2 will be in cell C5. Once we do that, we can then copy and paste the formula like this. And the remaining 2 formulas for number of hours and feet of tubing used will be taken care of automatically. If you look at any of those 2 formulas, you see the decision variable array remains the same. Without the dollar sign, it's going to change to B6 to C6 or B7 to C7. That is incorrect. All right, we're just going to keep the way it is. Okay, we have all the formulas we need for our simple Blue Ridge example. Now it's time for us to go ahead and solve it using our solver. Click solver. We need to fill in a few solver parameters. First of all is the objective. Well, that's our total profit. Where it is? It's in D6. That's it. And then the optimization in this case is maximization. By default is MAX, maximization. By changing cells, that's where we need to tell Excel where the decision variables are. We know that already, right? It's B5 to C5. All we need to do is to click and select those two cells. That's our changing variable cells. Now let's add constraints. Recall that we want to gather constraints of the same type together. In this case, we have only one type, so our life becomes much easier. Let's go ahead and click Add Constraint. Cell reference in our case will be resource used, D9 all the way to D11. Because all the constraints are the same type, we can do that. Otherwise, we have to do that one at a time. The constraint type by default is less than or equal to, well, let's keep it that way. And if you click this triangle, you are going to see some other types of constraint we can choose, like equation, greater than or equal to, integer, binary, and so on and so forth. And constraint is nothing but the right hand side value of constraint. They are in cell F9 all the way to F11. That's it. That's all the constraints we got. We're going to click OK. Otherwise, you're going to click Add to add more constraints. And a couple more things to take care of. First, well, we are going to check this box. Make unconstrained variables non-negative. That's how we take care of x1 or x2 greater than or equal to 0. And that's why we don't need to add a constraint earlier over here. And one more thing is to select the solving method. We're going to click this triangle. We're going to select simplex LP method. That's all we need. And then click solve. Well, what do we see? Not surprisingly, the optimal solution is 122 aqua spas, 78 hydrolysis, resulting profit $66,100. How much resource we have used? Oh, we've used all the 200 pounds, all the labor hours. What about tubing? We used 27 12 feet of tubing, which is less than what's available, 2880. Okay, so we're going to go ahead and keep solver solution. And I'd like you to generate two reports as well. One is answer report, the other is sensitivity report, which we're going to use later on for sensitivity analysis. Now click OK. We're all done. The solution for the Blue Ridge example is typical of solutions to optimization models in the following sense. First, of all the inequality constraints, some are satisfied exactly and others are not. Second, an inequality constraint is binding if the solution makes it an equation. Otherwise, it is non-binding. Third, the positive difference between the two sides of the constraint is called the slack. Now let's take a quick look at the answer report we generated earlier for the Blue Ridge example. Obviously, most of the information we see in the answer report is what we already know. Optimal solution 122.78, optimal profit 66,100. And what this means? It means the variables are continuous. All right, what about the constraints? Okay, like I said earlier, we used all the 200 pounds, we used all the labor hours, and we used only 27 12 feet of tubing. What does it mean? We have a slack of 168 feet of tubing. That's the leftover. and the slack for pump and labor constraints are nothing but 0. According to our definition, it means what? Pump constraint and labor constraints are binding in this linear programming problem. On the other hand, tubing constraint is not binding. If you recall, when we were trying to find the optimal solution to Blue Ridge example graphically, what do? We solve the two boundary lines simultaneously. Which two? Boundary line of pump constraint and boundary line of labor constraint. And that's exactly what it means. They are the binding constraints. They determine where the optimal solution is.